from my bachelor's institute, from my master's, and I'm also one of the co-leads for space safety and sustainability at the Space Generation Advisory Council. So I have like, I was thinking that to form a team, I can either, as Adriano mentioned, look into the group, or I will compose an email and participate in this as a team from Space Safety and Sustainability Project Group, and have 3 people from the project group who would like to work on this together for IEC 2025.
In this case, I would suggest that you guys, I mean, your team members, they can, everyone to register. I would suggest that. And whether if you are going to work in a team or maybe in different teams. So please spread the word.
I will.
Mahhad and everyone, the çignolet from the Union, Planetary Union, and I have a paper which has been accepted for IEC in Milano about volunteering, which is a settlement for 1,000 people to be built by the year 2030. And so I'm going over the following weeks and months to work on that presentation, and you are welcome to join the group. And I'll send you the mail.
Sorry, there was some noise, so I only understood half of your statement. I think you have a paper for IEC 2024 Milano. And
yes, and I have a paper about 1,000 people habitat, which I'm working, which is a ring of Stanford Torus. And so we are working on this presentation, and you are welcome to be in that group.
Yeah, I would love to. Let me write my email address in the chat, and you can.
Yes, please. Thank you. And now, okay.
Excellent. Great. Adriano, should I introduce Jerry again, or should we start with Jerry?
Yes, it is better. It is better because I restarted the recording. Therefore, the video will be this one that started 2 minutes ago.
So it's already recording now.
Will be discarded. Yeah. Otherwise, we have to mount everything. And okay. So go with your presentation of Jerry and make it short if possible.
Yeah.
Okay.
All right.
So, Ghanim, do you want to present Jerry or not?
Let me suggest this. Should you stop the recording now and start from over again? So it's easier.
No. Let's go. It's better because there was some information also useful for people who will watch to the video.
All right. So in this case, let me start again introducing Jerry. In this case, okay. So 1 minute, just let me find the file again. Okay, so let's start again our last webinar speaker, Jerry Stone. Jerry Stone is a freelance space presenter. He gave his first space presentation over 50 years ago, and now he runs Spaceflight UK and gives presentations on a range of topics on astronomy and space exploration all over the UK and abroad. He is a fellow of the British Interplanetary Society. He is also a member of the board of the Space Renaissance Initiative and the chair of the Space Habitat Committee and a member of the Council of the Federation of Astronomical Societies, the national body that supports astronomical societies across the UK. He is described as one of the leading speakers on space exploration and has spoken on space exploration at many venues, including the British Festival of Space, the Edinburgh Festival, the Farnborough Air Show, the Mars Society conferences in the UK, Europe, and the USA, Oxford University, the Palace of Westminster, the Royal Institution, the Royal Observatory Greenwich, and the World Science Fiction Convention. He ran a project at the British Interplanetary Society to re-examine the original space habitat studies. This became the Space Project Advancing Colony Engineering, which also resulted in a new concept called Island Zero, as described above. So, Jerry, the ground is yours.
Okay. Thanks very much. And this time I really can.
Okay.
Have an item to share.
Yes, we can see your screen.
Right. Now what I need to do is to just begin the presentation, and hopefully you can see a picture of me.
Yes, we can. Yes.
And you cannot see my notes underneath it.
No.
That's exactly how it's supposed to be. Okay, so as has been explained, I'm a fellow of the British Interplanetary Society and the Royal Astronomical Society, and I run Spaceflight UK. I have various other positions in different organizations, and I'm here today to talk about Island Zero, which I describe as a practical first step in the production of space habitats. So I'm going to start by presenting the background and then describe a new approach on space habitats. I'll explain the proposal of Island Zero and particularly talk about simulated gravity in its operation, and then mention benefits and take any questions that you have. So the story begins back in the summer of 1969, just a couple of months after the Apollo 11 crew landed the first men on the moon. Gerard O'Neill was a professor of physics at Princeton University, and at the beginning of the new semester, he set up a special seminar for a group of new students, and he posed what was meant to be the first of a series of questions that they would investigate to increase their interest in physics. However, he later said, as it turned out, once a first problem was chosen for discussion, it so occupied us that we never had time for a second. Working out its ramifications would occupy O'Neill for the rest of his life. The question he asked was, is a planetary surface the right place for an expanding technological civilization? Well, the answer seemed to be obvious, but the students went off and did their research, and the answer that they came back with was no, not on a planetary surface, which means not on the Earth, where we seem to be doing fairly well, but also not on the moon, not on Mars. Why? Because there were actually two reasons. The main reason was that any planetary surface will lose the sun for 50% of the time. And you can't turn the sun's energy into electricity. So you need an alternative source of power. On Earth, we have days that are on average 12 hours of sunlight. On Mars, they're 12.25 hours of sunlight, because a day on Mars, called a sol, lasts for 24.5 hours. But on the moon, daylight and nighttime both last for 2 Earth weeks. So you definitely need a source of power during that time. An additional problem for a permanent settlement is that on the moon, the gravity is only 1/6 that of Earth, and on Mars, it's 1/3. So over a long time, they will both result in major medical issues with the human body. So where should a structure be built if it won't be on a planetary surface? Well, to answer that, we need to go back 250 years. If this is the Earth and this is the moon, well, the orbit of the moon will actually be an ellipse around the Earth, but that can be calculated quite accurately. However, if you add one more body to the situation, the complication is incredible. And mathematicians labored for ages to come up with an answer to what was known as the three-body problem. Well, in 1772, a series of answers was worked out by Joseph Lagrange, and so they're known as Lagrange points. If you draw a line through the Earth and the Moon, L1 is between them, L2 on the opposite side. Now, normally, something closer than the Moon will go round faster. Further away, it will lag behind. But at these points, the combined gravity of the Earth and the Moon means they will stay in the same relative positions. There's also L3 over the other side of the Moon's orbit, but frankly, that's not a lot of use to us. However, these 3 points are unstable. If you start to move away, you will continue to move away, and so you need fuel for station keeping. However, there is also L4 and L5. These are both at the Moon's distance, 60 degrees in front of it, 60 degrees behind, and they are stable. So a number of designs were produced for possible habitats that could be constructed at these points, including the one at the top left, which I think looks rather like a 1950s lampshade. But the most useful designs were the sphere, the torus, or ring, and the cylinder. And a number of designs were produced based on these 3 shapes. So this is the one based on the sphere, which is in the very center of this painting, which is now 50 years old. Wow. And that's the habitat structure itself, where the people live. Moving out from the center, we have the large ring mirrors, which bounce sunlight off the ring of mirrors that surround the sphere. Then there is a whole string of rings which are used for agriculture. And then at the end of the central column are manufacturing and processing facilities, plus large radiators to get rid of waste heat. Now, what the painting does not show is the large solar panels needed to provide electricity for the unit. So as I said, the sunlight is bounced off the mirrors through these large ring windows. And if we look through them to the inside, we can see it's an inside-out world. There'd be houses, workplaces, schools, a hospital, sports centre, and other leisure facilities, plus public transport, everything required for a town of 10,000 people. As you can see, we take and grow earth plants and trees. We could also take bees to pollinate the plants and to make honey. But we could leave wasps behind so we can have our barbecues in safety. Now, having said that, just a couple of years ago, I found out that actually there are reasons why you might want to take certain types of bees to increase the pollination of plants, but not the stinging varieties. And we could certainly leave mosquitoes behind. So you can understand from this that the ecology is obviously an area that would be extremely complicated and would need very careful study and consideration. It'll probably be the most complex part of the entire project. So as you can see, agriculture wouldn't take place within the main habitat area, but in separate agricultural rings. Now, it would be possible not just to have several crops growing in adjacent areas, but the same crop can be grown at different stages. This is because, unlike on Earth, where usually a given crop only reaches maturity and can therefore be reaped once a year, here there won't be an overall pattern of seasons. So if you have something which grows over just a 3-month period, you can have 4 crops per year. So with 2 sets, 50% out of phase, we could reap corn every 6.5 weeks. Similarly, we could have fresh strawberries all the year round. We wouldn't need cattle for beef. Now we know that we can synthesize meat, which we didn't know about back in the 1970s. But probably we would have dairy cows for milk. We might also have chickens for eggs and pools of fish. Now, following on from this design, NASA sponsored a symposium in 1975, which produced this ring design. This would also hold 10,000 people. So it is at a level designated Island 1. But a design for a ring habitat was also produced that was much larger, that could hold 100,000 people, known as Island 2. And then there are the O'Neill cylinders. So before that, I just mentioned that we could build inside the habitats using mooncrete, that is lunar concrete, although the Scandinavian settlers might prefer to wait until enough trees have been grown in order to build their houses out of wood. So there's a view along one of the rings, and like the spherical habitat, we could have a river along the middle, although it would need to be pumped to flow. So here are the cylinders, and they are envisaged as twin cylinders linked together and counter-rotating, so there would be no overall torque. These are huge, 4 miles in diameter and 20 miles long. So agriculture would be carried out in the ring of small cylinders that you can see at the front of each of the main ones. So again, the same crop could be grown in separate cylinders at different parts of their growth cycle. And it was calculated that even larger versions could be constructed that would have a land area of 20,000 square kilometers. That's half the size of Switzerland. As you can see, the cylinders have alternating areas of land, called valleys, and windows, called solars. Sunshine would reflect off the main mirrors through the solars to the valleys on the opposite side of the cylinder. If you cut through one of the cylinders, you can get an idea of scale. The smaller units would need sprinklers for rain, with the advantage, of course, that you can time that when it's convenient for you. But here you would get natural clouds forming and natural rain. At the ends, you could go mountain climbing, with the additional benefit that as you go higher, the gravity reduces as you're closer to the center line, making it much easier to reach summit. Gliding would be another sport, and close to the center line, human-powered flight. Here's a view along one of the cylinders. And by adjusting the angle of the mirrors, you can actually produce different seasons. Now, as there are twin cylinders, you could have summer in one cylinder and winter in the other. So for a 50-mile trip by an automatic vehicle, you could nip over there to go skiing if you wanted to. You can get an idea of scale from the bridge that you can see in the center here. But now let's go back to the other end of the scale with the Island 1 design. Now, these would not be constructed out of material ferried up from Earth, because the cost of launching from Earth would be so prohibitive. Even with Falcon Heavy booster, and Starship is coming online, which will reduce costs even more. So where would we get the material from? And the answer is mostly from the moon. We'd also get some material from some asteroids. Now, from the Apollo project, we know what lunar soil and rocks consist of. There's a huge amount of oxygen for people to breathe. Also huge amounts of silicon for windows and glass fiber. There's also large amounts of iron, aluminium, magnesium, and other things. Titanium in Earth soil is about 1%. In Apollo 11 samples, it was 5.9%. The moon has another advantage, I should say two other advantages. No atmosphere, so if you're launching something, there's nothing going to slow it down, and solar power, which means we can make use of an electromagnetic launcher known as a mass driver. So this would send the material out to space without needing rockets. And it also would not need mining the moon, just scraping the surface with a bulldozer. It was estimated that a structural mass of 500,000 tons would be needed, but this would only need a volume 530 meters square by 5 meters deep. And to do this during 80% of the lunar day would take under 18 lunar days. And then we'd send it out. My calculations show that sending out 125 kilos of material at a time, then with just one load being sent every 10 seconds, it would take 35 lunar days. So the bulldozer could easily keep up with this. In fact, it wouldn't be quite as straightforward as that, as some work would be done on the moon itself. For example, on Earth, glass panels are made as float glass with molten silicon floating on a layer of molten tin and then cooled and cut to produce flat glass panels. Now, obviously, this has to be done under gravity so that the silicon will float on the tin, which is why it's called float glass. Well, there actually isn't much tin on the moon, nor lead, which also has a low melting point, but there is aluminium. So silicon would be separated, the glass produced, and the finished panels sent out. And how big would a mass driver have to be? As you can see from this painting, it wouldn't be a continuous solid line. You'd have accelerators spaced out that would pull on the payload as it went through, and also it would give you time to adjust the trajectory. That, of course, would all be done completely automatically. So the first demonstration mass driver, built by Gerard O'Neill and some of his students, produced an acceleration of 33 Gs in a few seconds. But to launch from the moon, it would have to be nearly 9 kilometers long. Mass driver 2 produced 500 G, and a lunar launch version would have to be nearly 600 meters, much smaller. But mass driver 3, producing an astonishing 1,800 Gs, would only need to be 180 meters. Actually, though, we'd probably work more with something like mass driver 2, so that we have plenty of time to do course corrections. So if we come back to Island 1, Gerard O'Neill deliberately restricted the design in 2 ways. Firstly, by cost, which had to be no more than the equivalent of Apollo. So that no one can say, well, it's a nice idea, but we can't afford zillions of trillions of dollars. You also limited it by technology. This had to be capable of being built by what was available at the time. So nobody could say, well, it's a nice idea, but it depends on this and this and this that we haven't invented yet. So the point is that given the initial funding and the will to go ahead, this could have been started in the 1970s. So why wasn't it? Well, although most of the material was intended to come from the moon, we still needed the initial infrastructure to begin the development, which would mean launching material and equipment from the Earth. And this service was intended to be provided by the Space Shuttle, which was originally expected to fly up to 50 times a year, drastically reducing the cost of getting into orbit. But in reality, the low flight rate and high cost of maintenance meant that this simply wasn't possible. However, a few years ago, I thought that we've made many advances since the 1970s. We have improved materials, new alloys, new materials such as graphene and carbon nanotubes. We have improved processes such as 3D printing. And our capabilities in computing and robotics are many orders of magnitude beyond what we had back then. So I thought if we were to start this project now, we could do it more efficiently and relatively cheaper. So I made a proposal to the British Interplanetary Society to set up the Space Project. Study Project Advancing Colony Engineering. That's my sense of humour. I have to say, though, that I do really prefer the term settlement rather than colony, but I needed it for the acronym. So I gathered a group of volunteers, and we worked on this for some years, eventually producing a special edition of the Journal of the British Interplanetary Society, which was diverted entirely to our studies. I began the project not by setting goals or saying what topics should be covered, but by asking the team members to come up with questions that would need to be answered as we progressed. I put the first two questions to the team myself. I said, all habitat designs have assumed that they will rotate to 1G. But do we need 1G? How about 0.9G, 0.8, or even less? There would be less stress on the structure, meaning it wouldn't need as much material for its construction. There would also be less stress on its inhabitants, on their cardiovascular system, their muscles, and their skeletal framework. They would be healthier, and over time, they'd live longer. They would also grow taller to a degree. We'd have to take that into account in the architecture, with higher doorways and ceilings. However, an associated question is, how much can gravity be reduced before it becomes a problem rather than a benefit? And the answer to that is nobody knows, because it's never been done. But we will need the answer in order to finalize the designs for the main habitat. I also pointed out that it is obvious that we wouldn't start by building an Island 1 habitat straight off. First, we need to extract the raw materials from the moon. Then we need to process these materials into the constituent minerals. Then manufacture the components that would be needed, girders, panels, etc. And finally, we need facilities to carry out the final assembly. And while all this goes on, even while these facilities are being constructed, we'd need somewhere else, somewhere to house the workers who will be doing all this. So before looking at Island 1, 2, or 3, we went the next step down the pyramid and came up with a concept which will answer both of my questions. And we designated this unit as Island 0. They would be relatively small, low cost, but could have many users and many uses apart from building Island 1 and larger structures. So the aims of Island 1 should be that it's constructed from modular components. So you can save by making the same part over and over again. Plus, some parts would be manufactured on site. People would live under simulated gravity. Although when you're out in open space, you'll be weightless, Island 0 would rotate. So it's inside, they would be under simulated gravity, particularly important when sleeping, which would be the greatest portion of their day cycle. And although we've had people in space for 60 years, this has never been done before. And it should also involve growing food on board and involve development of demonstration manufacturing facilities to process material to construct examples of habitat components. So I've referred to these units as porter cabins in space. But why have simulated gravity? Well, it would be easier just to have the unit operating under weightless conditions, like the International Space Station. The big problem is the detrimental effect on the human body. Without operating under gravity and having the body work against gravity, the following issues arise. Blood flow is no longer pulled to the lower part of the body. As a result, the lack of gravity causes fluid shifting to the upper part of the body. Muscles no longer have something to push against, and consequently, they weaken. The skeletal structure itself also weakens from not having to push the body upwards against the ground. This results in effective osteoporosis, which is a major study on the ISS. The cardiovascular system also has less work to do, and so the heart weakens. The heart actually changes shape from an oval, like a water-filled balloon, to a round ball, like an air-filled balloon. And recent studies by a NASA biologist suggest that spaceflight even compromises the immune system. And it's because of all this that everyone on the ISS has to carry out 2 hours of exercise every single day. Despite this, they are still relatively weak when they return to Earth. Some astronauts experience difficulty or even inability to stand as a result of lightheadedness and/or fainting. The exercise equipment has a mass of almost 2 tons, and so it would have cost about $100 million to launch it up to the ISS. Even using a Falcon Heavy, the cost would still have been almost $3 million. With Island Zero, it will not be necessary to launch this equipment or for everyone on board to use it for 2 hours every day. They can spend their time doing your more useful activities. So the basic units of Island Zero would be cylinders, 15 meters long with a diameter of 4.8 meters. They would be inflatable, like those already developed and launched on behalf of Bigelow Aerospace. To show the feasibility of this, when expanded, their proposed B330 module is planned to be 16.9 meters by 6.7 meters in diameter. Sierra Space is also working on and testing inflatable units, as are Max Space, whose founder, Maxime de Jong, built Genesis 1 and 2 for Bigelow Aerospace. The size was chosen as the units would fit into the cargo bay of Skylon, a fully reusable launcher that would take off and land on a runway. The revolutionary Sabre engines at the wingtips function both as a jet and a rocket and is under development in the UK. It has passed every single of the major tests that it has been put to, and it has got support money from the UK government and the European Space Agency. When operational, Skylon would be the long-term, dreamt-of single stage to orbit launcher and could bring launch costs down way lower than even those offered by SpaceX. The initial version would be unmanned. It would fly up automatically, take off on the runway, the jet engines pulling in air from the front, blasting it out the back, until when it reached about 5 miles, Mach 5 at 5 miles high, then the cells at the front of the engine would close off and it would use the onboard fuel and act as rocket engine. So this is one engine that can operate in two modes. The Skylon payload bay can accommodate a 4.8 meter diameter unit, but it's only 11.4 meters long. No matter if a 15-meter unit can be compressed to just 2.85 meters, or can be stored in the cargo bay. However, Skylon can only launch 15 tons, which would be just one module. Whereas Falcon Heavy, which didn't exist when I began this project, has an internal diameter very slightly smaller, 4.6 meters, but it can carry 63.8 tons into low Earth orbit. So it actually could take 4 modules at just under 16 tons each. Now, our original proposal assumed a ring of inflatable modules at 5 meters in diameter, 15 meters long when expanded. This would result in an even greater overall diameter of slightly more than 45 meters, a radius of just over 22 meters. But then I did some calculations on the simulated gravity produced by rotating the structures, depending on the speed of rotation and their radius. And I produced a table showing the equivalent G for different values. At a radius of 25 meters, even 0.3 RPM, 3 RPM would only produce 0.3 of a gravity. We would need 6 RPM to achieve 1 G, and that rate of rotation once every 10 seconds may not be that tolerable. So I thought, in order to have a reasonable rate of just 2 RPM, then in order to produce 1 G, we'd need to expand to 225 meters radius. But to have a ring with a slightly smaller radius of 200 meters would require a circumference requiring 84 15-meter units, far more than we actually need, and also means this, of course, would definitely no longer be a low-cost option. So how could we keep the number of modules down? Well, we developed an alternative in which the modules were no longer in a ring, but arranged radially. Now we can extend the tethers to give a 200-meter radius and add an outer connecting ring . So at 2.2 meters in diameter, this would provide a safety exit and also access to adjoining units, and it would also slightly help with stability. Now, this diagram is just to give an idea of the configuration. It's not to scale. So the modules would be divided into various levels, allowing for crew accommodation and areas for experiments. At the top of this module, the unit would be tethered to the central hub, which would consist of other modules set at right angles to the plane of rotation. And as parts of the central hub would be counter-rotating, then units attached to this could provide safe docking ports. This also shows the position of the main units with a safety ring. And to get between the levels, they wouldn't use ladders. There'd be spiral staircases fitted around the inside of the outer wall. The volume of one of these units would be 270 meters cubed. So with 8 units, you'd have 2100. Compare that with the Destiny module, which is the largest individual unit on the International Space Station. You can see that that's a lot smaller. And even the total habitable volume of the ISS is less than half that of Island 0. So this is a scaled diagram. In addition, we would need access tubes between the outer units and the central hub. Now, if the access tubes were straight, people and equipment moving out from the center would be falling at 0.9 G at the outer end. This might be acceptable, perhaps using ropes and pulleys when transferring equipment. However, they would hit the walls due to the Coriolis effect. But I thought it would be impractical and expensive to install lifts. So an alternative would be to have a series of tubes approximating a curve. A spiral option means people would transition to walking feet down when they reach the end of the tube. Now, you may think that this isn't really practical, but I can tell you it is not a new idea. It is actually almost 100 years old. A little while ago, I discovered that this had originally been proposed by Hermann Nudnung in 1928. Now, I'll come back to the idea of lifts later, but meanwhile, with some solar panels to provide power, here is Island 0. Nope. Oh, I'm so sorry, but the video isn't going to play on this. Never mind, don't worry. I'll show you a still of Island 0. In fact, you may be able to see it in the background behind me. Oh, sorry, it did play the second time. Well, it almost did. Yes! So I thought it was not radially, but actually horizontally. You'd get better use of the floor space and interior volume. And with the access tubes, so that's the outer ring connected, but if that outer ring connects to the lower floor, the access tubes could connect to the upper floor. Increasing the rotation from 2 to 3 RPM would mean that you could bring down the radius from 225 meters to just 100 meters, which means the unit would be shrunk from this to this. So it would not only mean shorter tethers, but only 2 access tubes, because it would be a shorter distance to travel from one module to another. And so therefore it would be considerably cheaper to manufacture. This also shows the central hub with solar panels and radiators. But further studies have shown the rotation rate of 2 or even 3 RPM is not necessarily required to achieve 1G at a rate that crew members can tolerate. Studies suggest that there is confidence that space settlements can rotate at up to 4 RPM, which translate to a system size of around 55 meters in radius to produce 1G, or even 6 RPM, giving a radius of just 25 meters, with inhabitants having some period of adaptation, but not a great difficulty in doing so. And these rates have been verified, particularly by Al Globus, who wrote The High Frontier, An Easier Way with Tom Marotta. It showed that in the right location, space habitats do not need to have huge amounts of radiation shielding, nor to only rotate at 1 or 2 RPM, and they can be much smaller than originally proposed. So I mentioned the right location, which in this case is equatorial low Earth orbit. Normally, items in low Earth orbit are inclined at some degrees to the equator. The ISS is at 56 degrees. But doing an orbit above the equator itself means there is far less space radiation, and we will probably not need special shielding. Yes, obviously, when we go further out, particularly out to L5 or in orbit around the moon, we will definitely need shielding, as we'll be outside the protection of the Earth's magnetic field. But 6 RPM, 25 meter radius, well, that takes us back to our original design. It wouldn't need an outer ring, just connecting sections between each cylinder. So it could look like this. So in this small version of Island 0, the hub would consist of 3 modules and would also have docking ports at each end. But personally, I think that this size, 1 rotation every 10 seconds, is too fast. At 4 RPM, the radius would be just 55 meters, much smaller than 200 meters. So zoom in shows this. The radiators actually would be at 90 degrees to the solar panels, as seen here. And at 3 RPM, it would have a radius of 100 meters, with a side view like this. Now, in all these views, the solar panels are the same size. However, perhaps an additional panel or 2 might be installed, as I've shown here, because the other power required would be for lighting and pumps for air and to remove CO2 in the outer ring. But I've added 3 extra solar panels in this view because before moving beyond low Earth orbit, we would add further main modules that would be slightly closer to the hub to produce 0.9G, 0.8G, and 0.7G in order to provide the medical research relating to having the human body living under lower values of gravity. And as you can see, these additional modules would each be 10 meters closer to the center. In view of this, we probably wouldn't actually need initial modules to give 1G because we already have the relevant medical information and any required control experiments could be carried out on Earth. So an actual 3 RPM unit would have a radius of not 100 meters, but 90, which would give 0.9 in the main modules, and modules at 0.8 G would be at 80 meters. And we need one opposite for balance. And at 0.7 G, they would be 70 meters out. And with this arrangement, we could carry out the research at different gravity levels simultaneously. This would enable us to gather the medical data needed in order to determine the best G level on the main habitats, and so to finalize their designs. In fact, Gerard O'Neill himself made it clear that experimentation for figuring out the right and best gravities for human and animal and plant physiology was crucial to long-term in-space living. But we wouldn't need probably the other 6 modules. They could be rented out to universities and research organizations to do additional medical studies, or to organizations to carry out other research, including material processing and other commercial activities. There is also the possibility of using one or more modules as a space hotel, generating even further income. So all in all, the Island Zero concept offers a lot of opportunities. Now, there is one other adjustment to the design that I've made. Let's look again at the access tubes. I originally said that installing lifts would be expensive, but recently I came up with a new idea. A simple lift, instead of being an enclosed cabin on cables, it would just be a platform moved on a rack and pinion. So the structure would look like this. And up it goes. It's interesting. So they could visit the modules at either upper or lower level, and also the central hub. And the reason I had a platform at top as well as the bottom is so that having reached the center, you just rotate your orientation and you can go effectively down the other side. Now, I was told fairly recently that inflatable units would require a thick wall, which would cut down how many could be launched at once. Now, this might be necessary in locations out at lunar distance, which would be above the Earth's radiation shielding. I'm still trying to obtain definitive information on this. But as regards to protection, let's look at the ISS. An alternative that would still allow a number of units to be launched together would be the use of expandable units. But in low Earth orbit, what about debris impacts? Well, in 30 years of operation, the space shuttle orbiters were struck by various pieces of debris, but only one penetration is known, only 1/10 of a millimeter wide, shown here. And it was on the radiators on the inside of the right-hand payload bay door, and not a full penetration of the craft's skin. Even if it had penetrated one of the orbiter's windows, the leak would have been far too small to present any risk to anyone on board. But there is an alternative to inflatable modules, and that is expandable units. So these could be used for the main modules, which would be expanded to give a flat floor, but by not fully expanding the upper panels, the unit would have a slight curve, which can follow the curvature of the outer ring. So this would still improve the efficiency of the internal volume usage. And for the lift shaft, it would be possible to use cylinders. So the resultant structure would change. If we look at the outer modules, they change from this being straight cylinders to this being curved units. There's another possibility for Island Zero, that a smaller version starting initially at 4 RPM could also be used to take crews to Mars. We could even adjust the rate of rotation during the journey so that when approaching Mars, it will be at 1.25 RPM and provide the equivalent of Mars gravity, 1/3 of Earth. So the crew will already be acclimatized to that gravity level when they arrive. Otherwise, they would spend about 7 to 9 months under weightlessness and then have 1/3 gravity on arrival. And NASA suggested that they may take 3 days to acclimatize before being able to go outside, which basically is wasted time. And on the way back, the spin rate will be slowly increased. Of course, we'd also need additional radiation shielding, but one advantage of the inflatable modules is that they actually provide more shielding than if they were made of metal. What else could the space habitats be used for? Well, 50 years ago in the 70s, we were talking about potential lack of resources on Earth. And also, though, about energy. Well, using the plentiful silicon from the moon, people on an island one could build large solar power stations that could convert sunlight and beam the energy down to Earth using microwaves to large receiving antennas, rectennas. The beam would be spread out so that at ground level, it would cover an area with a radius of 5¼ kilometers and be collected by screens that would gather the microwave energy, but would not block light. So birds could fly through the beams without being affected. So animals could graze on the ground below the rectenna. The microwaves would then be converted to electricity, which would be fed into the grid, providing about 10 million kilowatts at each site. Now, in January this year, NASA issued a major new report on space-based solar power, over 90 pages long. And it provides data on 2 reference designs, which would be standalone projects. That is, they would not be constructed out at L5. They would not need building a large space habitat first. However, although they would be constructed in multiple sections on Earth, which would then be launched into orbit, a unit such as Island Zero would be of huge benefit in housing the assembly crews. In addition, NASA is also promoting commercial activities in low Earth orbit. And again, Island Zero units would be of great use in this respect, because you could still do microgravity work, i.e. in weightlessness, carried out in the central hub, while allowing the crew to spend their other time off duty and sleeping under simulated gravity. So Island Zero can achieve a lot. In fact, it can achieve several goals set out by the National Space Society. 5 years ago, they published the 3rd edition of their Roadmap to Space Settlement, and it stated, a future that includes the expansion of humanity into space is vastly preferable to one in which we are limited to resources of Earth. This fits 100% with the thinking of Gerard O'Neill. It then explained the purpose of the document, saying, this roadmap describes the major milestones to be met. And a number of these milestones can actually be met by the implementation of Island Zero. They include continuous human occupancy in low Earth orbit. Now, it could be said this has already been achieved with the ISS, but the milestone says achievement will include at least one commercially owned and operated low Earth orbit station, which could be done with Island Zero. Development of a space tourism in this industry, as I've said, that can also be achieved with Island Zero, as can the establishment of in-space commerce by private companies. Another milestone is specifically the use of rotational artificial gravity for habitats and industry. And I have to say here that I don't like the term artificial gravity. Artificial gravity is what they have on Star Trek, where you can stand up on a floor which is actually traveling at 90 degrees to your direction of movement. So that's artificial gravity. What I'm suggesting is produced in Island Zero is simulated gravity. In any case, artificial gravity is not even science fiction, it is science fantasy. And then there's also the development of an equatorial low Earth orbit settlement, which is exactly what I've just described for Island Zero. Back in 1974, in his first article on space habitats, Gerard O'Neill wrote, "It is important to realize the enormous power of the space colonization technique. If we begin to use it soon enough, and if we employ it wisely, at least 5 of the most serious problems now facing the world can be solved without recourse to repression. Bringing every human being up to a living standard now enjoyed only by the most fortunate. Protecting the biosphere from damage caused by transportation and industrial pollution. Finding high-quality living space for a world population that is doubling every 35 years. Finding clean, practical energy sources. Preventing overload of the Earth's heat balance." And he said this years before we got familiar with the concept of global warming. But also, as the resources available from the moon and asteroids far outweigh those on the Earth, and the living space generated from the construction of large habitats outstrips the global population increase, it means firstly that we will never run out of room, and as a result there will be no need for any nation to attempt to claim resources from others. In other words, the threat of warfare should be reduced. That means that moving into space will reduce war on Earth, and surely if there is any reason for going into space, that has to be it. This was effectively summarized in a quote from Frank White, who wrote The Overview Effect, about how people who have been in space are affected by their view looking back on Earth. He said, war and space exploration may be suitably mutually exclusive, because if one occurs on a massive scale, the other probably will not. And that can go either way. Obviously, we know which option we would prefer to see, and the development of Island Zero may well be the best way of moving forward in this activity. As for Island Zero itself, there are a number of benefits for this concept. It can be constructed using current technology, meaning right now. It can be launched using current boosters. It'll be rotated to produce simulated gravity, unlike anything ever launched before. It'll be able to operate at different gravity levels simultaneously. And as a result, it can be used to provide essential medical research. It can house crews involved in commercial activities, including space tourism, and acclimatized crews going to Mars and returning to Earth. Now, obviously, more work is needed to finalize the design, layout, and construction options. A major factor is this is not like a proposal for a new type of satellite or space telescope. A structure like this has simply never been built before and will result in people living and working in conditions never before experienced. It will therefore take some careful work in its detailed design. So I am putting together a proposal that either NASA or the European Space Agency carries out a feasibility study to verify the concept of Island Zero. Meanwhile, we have a title and a logo, which I actually have on a tie, which I've had printed. There you go, you can just see that. And bearing in mind that mankind's expansion into space could help reduce wars, it seems appropriate to slightly amend the logo. And we also have a slogan, courtesy of Blade Runner.
The chair to begin again, the goal that I have obviously had.
So if you'd like a summary file about Island Zero, then my email address will go into the chat, and by all means, send me a request. So I have submitted an abstract for the IAF conference in October, which will be in Milan. And I'm pleased to say that last week I received an acceptance. So I'm off to Milan in October. Really pleased. The only problem is that I won't have nearly as long to give my presentation as I have today. And I'll have to give an extremely short summary and encourage people to meet me or perhaps at the SRI stand to go into more detail. But if you know anyone who'd like to arrange a full presentation, then do please ask me. Now, there's some material which I have cut out because of the timing today, particularly on the Coriolis effect and why pouring a cup of tea on a space station may depend on which direction you're facing as to how it pours. But we can get onto that in the discussion. But for now, thank you very much.
Thank you very much, Jerry, for this amazing presentation. Of course, Island Zero is an exciting concept. I would like to start quick Q&A. I mean, we have already passed the time, so I will just ask one single question from my side before allowing everyone else to ask other questions. So very quickly, and here I'm going to focus only about Island 1 and Island 2. As you mentioned, maybe the technology is not going to be the limit. The readiness of the technology is not going to be the limit. The cost maybe is not the limit, but maybe the limit is with risk analysis. So looking at this unconventional project where you have rivers flowing, maybe through the generations, 10, 20, 30 years, there will be a malfunction in the rotation. And this will end the entire project because water will fall. Just a imagination, a single malfunction, and maybe a risk analysis, a general risk analysis will be extremely important.
Okay, but if you've got a unit with a mass of 500,000 tons, what would stop that rotating? You need a heck of a lot of energy to do that.
Yeah,
but it will require power, of course. It will require continuously pushing the system.
No. Once the system is up to speed, then it will carry on rotating. It will not need continuous power to keep it spinning.
Okay, yeah.
It's out in space. There's no friction.
Yeah, but however, I think that yes, it's a good answer, Jerry. And also we should think that probably there not will be any mechanic rotation gears and I mean mechanism. So therefore, it will be a unique piece of thing that it will be rotating without any attrition or things that will consume the materials and so on. However,
the only
I believe risk analysis is a very sorry, Jerry. Then I leave you.
The only bit might be if there's part of the manufacturing facility at the very end of the central hub, which is counter-rotating, if you actually want to have weightlessness. But then if you want to do processes in weightlessness, you could always just push off from the structure. And that's what you'll have.
However, no, what I wanted just to add is that risk analysis is a very good suggestion because especially a methodology called FMECA, the acronym is FMECA, that is the failure analysis. I don't remember exactly the meaning of the whole word. However, it means that each potential failure should be analyzed with relation to the cascade effect that each failure could have on the whole system. So this is something that is very, very important to do, but I believe that it is an analysis to be made in an advanced stage of the design.
Well, again, that would be part of the phase A study. to look into potential.
Yes, and in the phase A study, we should just understand by proper trade-offs if there are no, what can I say, show-stopping conditions that can
Yeah.
suggest
But,
not develop the project.
remember that Gerard O'Neill himself studied this for several years before coming out with his book. This is, I'm very pleased to say,
Yeah.
book that he signed for me in 1977.
It's also my Bible, my Bible too.
Yeah, that's not the
It's in
first.
Italian. It's an Italian version.
Oh,
Yeah.
very good.
Yes.
But this is the first edition from 1977 when he came to Britain to give a presentation. I was one of a small number of people who took him out.
Well, 1976 is in my edition is 1976. The High Frontier Human Colonies in Space.
So that's taken direct from the American edition then.
I don't know if you can read it. Maybe,
Very good.
maybe yes, maybe not.
Yeah.
Can you read it?
No, it's
Oh, hang on a bit more. Yeah. There
oh
we go.
yeah.
Very good.
Yeah, 1976.
Yeah. Okay, I have put my email address in the chat, so if anybody either wants to send me any questions or to request a summary, I'd be quite happy. You'll need to copy that off from the chat before we finish the meeting.
Excellent.
Yeah, another question came to my mind, always on the file of the technical questions. Do you think that the construction, the structure, the materials and everything will be the same in case of a low Earth orbit infrastructure, of a Lagrange point infrastructure, and a Starship to Mars structures? I think maybe we should try to think about what it must be different.
Yes,
Because I believe there are differences in terms of radiation,
yes,
cosmic radiation, in terms of micrometeorites and other kinds of things that can hit our.
Okay. So as regards what might hit it, out at L5, effectively nothing. Our surveys of space rocks is getting much better. NASA's current aim, I think, is to catalogue every item more than a meter in size, which can pass as a near-Earth asteroid. And if one of those was to hit a habitat, and even if it was to crash right through a window panel, and of course the window panels would be made of small triangles, so that perhaps if two were shattered, the rest would still be safe. But if that was to happen, then it would take at least 50 years for all the air to leak out. And in the meantime, of course, there'd be sensors on every panel, so we'd know immediately where to go to make a repair.
Mm-hmm.
What would be different between a unit in low Earth orbit and outer L5 is, of course, the extra radiation shielding. That's a must.
Yeah.
But it's been suggested that if we have a sort of net around the outside of the main structure, and that could be filled with additional rubble and so on, leftover debris from processing the lunar material.
Mhm.
And that would act as
Yeah.
egg
Some
shielding.
polymers also and something like that. I also see in the chat here, GUI just wrote, Milano, the importance of showing models.
Well, I hope to do that.
Are you thinking maybe we will have some mock-up, some model of Island Zero in Milan? Can we have it?
It would need to be produced because there is nothing that exists at the moment.
I know.
I'm
I
actually
suppose
looking
that, but no,
at,
take into account that Space on Essence could support a modest expense to produce this
well,
kind of.
fine. If I could,
I
see
mean,
for
let's
example, I
make
have already started to develop designs for units to be made on a 3D printer that could then be joined together to make a model
yeah,
of.
yeah. So please make a budget calculation. How much money? I hope it will not cost more than some hundreds euros or something like that. If that's true, we can make it. Why not?
If that can be taken to the IAC, that would be absolutely terrific, because I could show it during my presentation, and the rest of the time it could be on the SRI display stand.
Yes, yes.
Marvelous.
Let's think about. Okay.
Oh, definitely.
However, a wonderful presentation, really very much more rich than the previous ones that we have seen. I can see that you are improving each time.
Yes.
Adding more things, and it's very interesting about the cultivation and the vegetable and the farming and all this kind of discussion.
I briefly mentioned Coriolis effect. So if you are pouring there you go. So if you're pouring a drink into a glass or pouring a cup of tea, then as it goes down, of course, the Coriolis effect means that it will not go in a straight line.
Yes.
So it depends whether you're looking towards the direction of travel, in which case it'll come towards you, or if you turn around facing the other way, then you pour it and it will go further away from you.
Yes, yes. Luigina Ferretti explained it very much in a simple way in her webinar.
Right.
The gravitational attraction and the centrifugal force and all these kind of things. And centrifugal force is an apparent force, because the real force is the escape, the tangent force. Yeah.
On a snooker table would need to be curved.
Yeah.
Otherwise, if it's flat, you put a ball in the center and it will roll to one of the edges. And a piano, well, you can't curve piano strings, so they will all need to be set with the piano at 90 degrees to the roll of rotation, which means the pianist will be there with the piano in front of him, and he will look out to one side or the other to see his audience.
Yeah.
I came up with that when I was about 30.
I'm afraid in a few minutes we have to close, because at 7 p.m. we have another meeting.
Yes, indeed.
Going to start with LuiseHeuser, the space philosophy committee. Therefore, we have to close this meeting. But a few minutes we still can talk.
Well, thank you all very much for being here today. I hope you have found this interesting. And as I said, my email address is in the chat, so do send me any other questions that you have.
Okay, so Ghanim, I don't know if you want to close.
Yeah.
Yeah, I think that's it. That's actually the end of our webinar series. Our competition is actually about having an O'Neill type cylinder for hundreds of inhabitants. So I believe this is going to be really informative and a good starting point for our participating team. So thank you very much, Jerry, for
I
this
think that
presentation.
maybe sorry, Ghanim, maybe we will need at least one tutorial meeting, no, for all the participants in order to explain again the mechanism, what they are expected to do, and all this kind of thing. So maybe we have to schedule a meeting in I don't know, in 1 month or so. Now we will talk about that. Okay, so good.
I'd be happy
Yeah.
to be involved in that.
Thank you.
Excellent.
Thanks,
Thank you.
everybody.
Thank you, everyone. Thank you.
Ad astra. Bye bye.
Have a great day.
Bye bye.
Goodbye.